Liquefaction and Dam Failures by Daniel Diamata. Liquefaction is a state when saturated sandy soil loses its shear strength due to increased pore pressure and consequent reduction of effective stresses. Liquefaction is very misunderstood by geotechnical engineers. Many argue what the real meaning is. The history of dam failures and causes of liquefaction that caused Fort Peck, Baldwin Hills, Teton Dam, and Lower San Fernando Dam to fail will be observed. All four of the dams identified were hydraulic-filled earth dams that failed from different scenarios. More than 900 dam failures causes throughout the world have been collected and compiled into a database. The causes comprise earth dams, concrete dams, masonry dams, rock-filled dams, and so on. Figure 2a compares the percentages of these types of dams and shows that 66% of the causes are earth dams. The failure causes emanate from over 50 countries, US, India, and the UK. Figure 2b shows the geographic distribution of the failure causes. The US has the most causes, about 70% of the total population. The number only reflects how many failure causes are reported rather than how many failure causes generally occur. Figure 2c shows the percentages of subcases of quality problems for earth dam failures. 58% of quality problems are associated with piping the dam body or foundation. Overall, the most prevalent causes of earth dam failures are overtopping and piping the dam body or foundation. The main influence factor on overtopping is specificity of spillway capacity. For piping the dam body or foundation, the most single adverse factor is crack, which can be caused by differential settlement, material shrinkage, foundation defects, and imperfect interface. The Fort Peck Dam controlled floods and will facilitate navigation for hundreds of miles along the Missouri River. This dam had a very unique way of controlling seepage. Sheet pile was driven to the ground, 17,000 tons of it. This was anticipated to form a 10,000-foot long wall deep inside the center of the dam. The center of the dam was made of fine-grained materials, and coarse materials were used for the outer sections. On the upstream face of the structure, large stones transported 30 miles to the site by rail were used as riprap. Workers noticed that the dam appeared to be shifting on the east side of the dam on the evening of September 21, 1938. 5 million cubic yards of earth slid from the upstream side of the embankment into the river. The following day, engineers studied the catastrophe and figured out that the shearing force at the base of the dam had been too great for the foundation. The dam was located in the Baldwin Hills of California. The dam was constructed in 1951. It was 71 meters high and 908 meters long. The Baldwin Hill Dam was ideally for water supply. The reservoir capacity was 897 acre-feet, and the surface area was estimated at 20 acre at the spillway crest elevation of 477.5 feet. The dam was constructed of earthen materials in line with asphaltic pavement. The reservoir was rectangular in shape and encircled by engineered embankment. On the northeast corner of the reservoir, a drain pipe was designed. The purpose of the drain pipe was to catch water just in case the reservoir inadvertently overfilled. The reservoir also had a drainage system that was engineered and designed to remove poor water pressure, which penetrated the asphaltic lining of the reservoir. It penetrated the lining through the cracks resulting from differential settling. On December 14, 1963, the newly constructed Baldwin Hill Dam reservoir failed. Unfortunately, 5 deaths were documented with an extensive amount of flood damage. Since the failure occurred in 1963, geologists and engineers have been investigating this crack and similar cracks nearby. All the cracks investigated were known to be surface expressions of deep near-vertical faults. The disaster occurred as a result of displacement along faults in consolidated sediments under the reservoir. It's believed that these displacements led to the rupture of the protective clay lining that covers the floor of the bow-like structure. The 10-foot thick lining was designed to isolate the sandy soft foundation rock from leakage of the reservoir water. The designers didn't think it was possible for offsets along one or more of the buried faults were great enough to destroy the lining. Responsibility for the disaster has never been formally fixed. California's Department of Water Resources provided a narrative of events on the day of the disaster, stating it was the result of an unfortunate combination of physical factors. Sitting on the flank on the sensitive Newport-Inglewood fault system with its associated tectonic restlessness, at rim of a rapidly depressing subsidence basin on a foundation adversely influenced by water, the reservoir was called upon to do more than it was able to do. According to the City of Los Angeles, this wasn't the reason of failure. They believe injection of fluids into the ground for oil recovery and waste disposal triggered surface faults. The report shows the geologic structure section throughout the Baldwin Hills Inglewood area and the Inglewood oil field. The Los Angeles Department of Water and Power Engineers discovered a more widespread and large-scale form of ground surface movement. As early as 1943, when comparison of leveling surveys indicated that elevation changes were taking place in the area, the tectonic theory is open to objections. The Teton Dam was located in Fremont County, Idaho. The dam was originally called for an earth dam with dimensions of 93 meters high, creating a 27.4 kilometer long reservoir with a 333 million meter cube capacity. The area had basalt rock foundation that was soon to be found as a problem for the construction integrity of the dam. On June 3, 1976, during initial filling, small springs were noticed downstream of the dam. This was taken as an identification of water seepage, and the face of the dam was examined. On June 5, 1976, seepage was discovered on the face of the dam, and caution was taken to make sure safety of the people and dam were ensured. The workers tried to fill the newly created holes with rubble. This didn't work, and the voids continued to grow. Hope was then abandoned, and the dam had no chance of survival. A vortex was observed an hour before the failure of the dam. The dam then failed, and at the peak release, the flow was estimated to be 28,000 meters cubed per second. Water rise to be 22.9 meters high as it rushed down the valley. 14 deaths were reported from the flood, and large areas of cropland were destroyed along with livestock. The reason the dam failure is still unknown. The failure occurred likely because it was visible. Some possible reasons of failure were piping due to cracking. Post-failure test data from the left embankment soil indicated that differential settlement could have occurred. Hydraulic fracture due to anchoring could have occurred, and the deep key trenches due to lateral stress. The U.S. Department of the Interior investigation concluded that neither of these was likely what caused the failure. Flow through grout curtain due to the fractured nature of the foundation rock is also a possible cause of failure. The grout curtain was tight, and this could have allowed water to flow into Zone 1 core, resulting in internal erosion. Figure 5 shows Zone 1. Due to the fractured rock base, water could have entered Zone 1 through ungrouted fissures. Water would naturally move in the direction of lower hydraulic pressure on the downstream of the dam. San Fernando Dam is located in San Fernando Valley of Southern California. A massive landslide occurred on February 9, 1971. An earthquake with a magnitude of 6.6 caused several longitudinal cracks, a very steep slide headscarp, and a marginal freeboard at about 1.5 meters. The lower San Fernando Dam was a 43-meter high dam with a reservoir capacity of about 25 million meter cube. According to SEED, good moisture control and better compaction practice were conducted during the construction of the lower San Fernando Dam, and then therefore it anticipated that lower San Fernando Dam was well built on well compacted soil, and it is unlikely that the soil structure of the dam was at loose state. A laboratory investigation was concluded to evaluate the causes of this slide. Shown in Figure 6 are the pre- and post-failure cross-sections of the lower San Fernando Dam. SEED concluded that the primary cause of the upstream slide in the lower San Fernando Dam was liquefaction and the development of very high pore pressure towards the end of the earthquake shaking. An extensive zone of hydraulic fill near the base of the embankment and upstream of the clay core, so that much of the hydraulic fill was in a liquefied or very low strength condition, while no liquefaction or strain softening occurred in the aluminum soil beneath the dam. The Baldwin Hills and Teton Dam was thought to have failed from cracks in pipes induced by overcompaction, as stated earlier. It was believed injection of fluids into the ground for oil recovery and waste disposal triggered surface faulting for the Baldwin Hill Dam failure. Hydraulic fracturing might have caused liquefaction for the Teton Dam failure. There's really no telling what caused liquefaction for these dams. And now since they're destroyed, it might be a mystery forever. There's no telling why the real reason dams keep failing due to liquefaction and how to prevent it. Much more research needs to be done to conclude the reasoning so dams in the future will not fail.